Okay, so just for fun, for some definition of fun, let's take a look at a problem I ran across that will involve skills in two of my other videos, and that's factoring depressed quartics and denesting nested radicals. So we want to solve this equation. Square root of 4 minus x equals 4 minus x squared. I came across this problem via one of Cybermath's video, that's SYBER. As we'll see, solving this equation requires squaring both sides, which results in a quartic equation. Now, Cybermath had a neat method using a parameter instead of 4 to first alter the equation into a quadratic equation in that parameter, and then eventually solving for x to get all four potential solutions. And then, of course, because of the squaring, all those solutions needed to be checked if they're extraneous or not. However, I noticed that the quartic polynomial that arises is precisely the type of depressed quartic we can try to factor into two quadratic expressions. Then it turns out that plugging the potential solutions back into the original equations results in nested radicals, which, in the absence of a calculator, we can denest and simplify to check them. We'll get into all that, and then we'll see how it works with a general parameter instead of 4, and finally we'll explain what happens with the solutions as that parameter changes. So let's get going. First, let's start by squaring both sides. 4 minus x equals 16 minus 8x squared plus x to the fourth. Getting everything on one side, we get 0 equals x to the fourth minus 8x squared plus x plus 12. So we have an equation with a depressed quartic polynomial. That is, a quartic polynomial with no x cubed term. So just to be thorough, let's see if we can factor out a nice linear factor. The rational root theorem tells us that if there's a rational solution to this equation, then it will have this form, m over n, where m divides the 12 and n divides the leading coefficient, 1. So that means we're going to have these as candidates, plus or minus 1, 2, 3, 4, 6, and 12. Now, I'm not going to check all these, but suffice to say, none of those work. So this is a prime candidate for factoring this depressed quartic into the product of two quadratic polynomials. So let's recall how to factor a depressed quartic. If we have something like this, x to the fourth plus px squared plus qx plus r, and we want to factor it into these two quadratics, x squared plus bx plus c, x squared minus bx plus d, then we need to find c and d so that c is less than d. C times d equals r, the constant term. Our possibilities for b needs to be q over d minus c, and that needs to be an integer if we're factoring with integer coefficients. And then we have this last requirement that p plus b squared has to be equal to d plus c. And technically, we're only worried about getting the absolute values of those equal, and we'll worry about the signs later. So just to be thorough, let's go through all the factor pairs of 12 in this case. And so this is our p, this is our q, q is 1, and r is 12. So we need to find a c less than d, so that cd equals 12. And so let's go through our pairs. 1 and 12, 2 and 6, 3 and 4. We're going to stick with the positive versions. Since they multiply to a positive 12, they have to be the same sign. So let's take b to be q, which is 1 over d minus c. Well, d minus c here is 12 minus 1, which is 11, 1/11th. Not an integer, so we don't worry about that. 6 minus 2 is 4. It's 1/4, so that's out of the picture. 4 minus 3 is 1, so we have 1 over 1, which equals 1. That checks out. That's an integer. So that's our candidate. Now we're going to figure out what p plus b squared is. Well, p is, in this case, negative 8. Negative 8 plus 1 is negative 7. Now, does that equal to d plus c? D plus c is indeed 7. Now, again, we're really only concerned that they are equal in absolute value, and so that checks out. And what that means is that d and c are the same sign. That means they have to both be negative. Now, c has to be less than d, so c has to be the negative 4, and d is negative 3. That means our quartic, x to the fourth minus 8x squared plus x plus 12 equals x squared plus x minus 4, because b is 1, and x squared minus b, which is minus x minus 3. So setting that equal to 0, we have two quadratic equations that we can solve. So for the first equation, x squared plus x minus 4 equals 0. We can use the quadratic formula to solve this. Let's call these two solutions x1 and 2, and they are negative 1 plus or minus square root of 17 all over 2. So x1 is the plus version, x2 is the minus version. For the other one, x squared minus x minus 3 equals 0. Same deal. We're going to call these x3 and 4. And that's 1 plus or minus the square root of 13 all over 2. So those are our four candidate solutions. Since we squared both sides, we need to check them to make sure that they're not extraneous. That means plugging these into the original equation. Let's start with x1 and 2. So to maybe save time, I'll plug in both with the plus minus and try to keep track of the signs as we go. If the signs flip, I'll write it as minus plus. The right-hand side is pretty straightforward. It's just 4 minus x1 or 2 squared. That's 4 minus negative 1 plus or minus the square root of 17 over 2 squared. And this is negative 1 plus or minus the square root of 17 over 2. Plugging x1 and 2 into the left-hand side, we're going to get our nested radicals. So we're going to get the square root of 4 minus negative 1 plus or minus the square root of 17 all over 2. So we can get a common denominator of 2 on the inside of that and bring it out as a 1 over square root of 2. And that's times the square root of 9 minus or plus the square root of 17. So again, that minus version comes from plugging in x1, and the plus comes from plugging in x2. So we're going to denest this in a general way, and then maybe we'll take some shortcuts later on. So to denest this radical, remember, we need to find two numbers, m and n, and we want m greater than n, such that the product is 17, and their sum is equal to double this number here, which is 18. If we can find those numbers, then our denesting is going to be m over 2 square root minus or plus n over 2 square root. And we need m to be bigger than n for precisely the case when there's subtraction there. Well, 17 times 1 is 17, and 17 plus 1 is 18, twice 9. So that means the square root of 4 minus x1 or 2 is 1 over square root of 2 times the square root of 9 minus or plus square root of 17, and that's equal to square root of 17 over 2 minus or plus the square root of 1 over 2, or 1 over square root of 2. And you can see that we can bring that square root of 2 back inside, and we have square root of 17 minus or plus 1 over 2. Or I'm going to rewrite this as minus or plus 1 plus the square root of 17 over 2. So remember, our right-hand side is here, and our left-hand side is here. For those to be equal, well, the 1 has to be negative, and the square root of 17 has to be positive. The only way that happens is by plugging in x1. So x1 is a solution, but x2 is not. Let's do the same thing for x3 and 4. So again, our right-hand side, 4 minus 1 plus or minus square root of 13 over 2 squared. And that is the same as, from a bunch of simplification, that becomes 1 minus or plus square root of 13 over 2. Again, that minus, the top symbol there, comes from plugging in x3, and the plus comes from plugging in x4. The left-hand side, again, involves denesting radicals. The square root of 4 minus 1 plus or minus the square root of 13 over 2. So just to be different, I'm going to factor out a factor of 4 from the square root, making it a 2 on the outside. What that does on the inside is it gives us 14 minus or plus 2 square root of 13. Now I do this because denesting a radical with a 2 in front of that inside radical is a lot easier to do. All I need is an m and an n, m greater than n, such that mn equals 13. and m plus n equals 14. And then that would just denest to square root of m minus or plus square root of n. 13 times 1 is 13, and 13 plus 1 is indeed 14. So 13 and 1 are our two numbers. So this becomes 1/2 times square root of 13 minus or plus square root of 1, which is just 1. And so that's minus or plus 1 plus the square root of 13 over 2. So comparing the left-hand side and the right-hand side, if this is equal to 1 minus or plus square root of 13 over 2, well, the 1 has to be positive. So that's from plugging in x4. And also, the square root of 13 has to be positive. That's going to have to come from plugging in x4 as well, too. So x4 is a solution. So just to reiterate, our only two solutions are x1, which is -1, plus square root of 17 over 2, and x4, which is 1 minus square root of 13 over 2. That's it. Let's look at solving the same equation. Let's use a parameter instead of 4. Let's look at the square root of a minus x equals a minus x squared. Now, when we square both sides, we're still going to get a depressed quartic on one side, x to the fourth minus 2ax squared plus x plus a squared minus a. Now, as I mentioned before, you can rewrite this polynomial in terms of a and write it as 0 equals a squared minus 2x squared plus 1, a plus x to the fourth plus x, and then solve this for a using the quadratic formula. And you'll get two possibilities. A equals x squared plus x, or a equals x squared minus x plus 1. So from here, we could plug 4 back into a in both of these and solve the original equation. So this is a really slick way to do it. You'll get the same quadratic equations that we got before. X squared plus x minus 4 equals 0, and x squared minus x minus 3 equals 0. We could also just leave the a alone and solve these quadratic equations as is to get our 4 candidate solutions in terms of a. As we'll see, which ones of those are solutions to the original equation depends very much on what a is. Regardless, the method here of switching the equation into a quadratic in a, very cool tool to have in your tool belt. And probably it's more versatile than this factoring depressed quartics. But let's try to factor the quartic with a in it anyway, just to see if it works. Let's go back to our original quartic equation after squaring both sides. Now be aware that if a is less than 0, then you're going to have an a less than 0 minus x squared. You're going to have a negative number on the right-hand side, and so there's not going to be any real solutions in that case. So for the most part, I'm going to be taking a to be positive here. So remember, if we want to factor this depressed quartic, we need c less than d. So cd equals a squared minus a. Well, a squared minus a is a times a minus 1. So let's just take that. Let's just take a minus 1 as c, and a is d. Now b, if it's going to work, it's got to be an integer. It's going to be q divided by d minus c. That's got to be an integer. Q here is still 1, so d minus c has to be equal to 1. Well, d minus c here, a minus a plus 1 is 1, so b is 1, 1 over 1. That checks out. And then we need p plus b squared. Well, p is negative 2a, so this is just negative 2a plus 1. What's d plus c then? 2a minus 1. So these two are equal in absolute value, but just like in the case with a equals 4, we need to use the negative versions of c and d here. So we need c to be equal to negative a and d to be equal to negative a plus 1. So c is less than d. Well, with that all done, we've got x to the fourth minus 2ax squared plus x plus a squared minus a is going to be equal to x squared plus b. B is still 1, so x squared plus x plus c, which is negative a, and x squared minus x plus d, which is negative a plus 1, which matches what we would have gotten from these. Okay, let's solve these. First, we've got x squared plus x minus a equals 0. And so that gives us x1 and 2 is negative 1 plus or minus the square root of 4a plus 1 all over 2. And from x squared minus x minus a plus 1 equals 0, we're going to get x3 and 4 to be 1 plus or minus the square root of 4a minus 3 over 2. So those are our 4 candidate solutions. Let's check them as we did before. Let's plug x1 and 2 into our original equation. Let's do the right-hand side. A minus x1 or 2 squared. Turns out that that's equal to negative 1 plus or minus the square root of 4a plus 1 all over 2. And our left-hand side, which is the square root of a minus x1 or 2, factor out a 1/4 again as a 1/2 outside of the square root. And inside the square root, we have 4a plus 2 minus or plus 2 square root of 4a plus 1. So to denest this, we need two numbers, m and n, m greater than n, so that mn equals 4a plus 1 and m plus n equals 4a plus 2. Well, guess what? 4a plus 1 times 1 is 4a plus 1, and 4a plus 1 plus 1 is 4a plus 2. So we could just use 4a plus 1 and 1. 4a plus 1 is bigger than 1, so we're good to go there. So the left-hand side, denested, will be equal to 1/2 times the square root of 4a plus 1 minus or plus 1. In other words, minus or plus 1 plus the square root of 4a plus 1 all over 2. And we got to see, does that equal the right-hand side? The right-hand side is negative 1 plus or minus the square root of 4a plus 1 over 2. It's only equal when our 1 here is negative from plugging in x1. And the square root of 4a plus 1 has to be positive, so that's from plugging in x1 as well. So we see that no matter what, x1 is a solution. And x2 never is. Now, plugging in x3 and 4 into our original equation has some subtleties. So first note that x3 and 4 are really only real when a is greater than or equal to 3/4. That's because if a is less than 3/4, we're going to have a negative number underneath the square root. So the right-hand side of the equation isn't too bad. I'll put it here. A minus x3 4 squared. We get 1 minus or plus square root of 4a minus 3 over 2. And here's the left-hand side. A minus x3 4 underneath the square root. That's going to be 1/2 times the square root of 4a minus 2 minus or plus square root of 4a minus 3. So again, we need m greater than n greater than 0, such that mn equals 4a minus 3 and m plus n equals 4a minus 2. So we know that 4a minus 3 times 1 equals 4a minus 3, and 4a minus 3 plus 1 equals 4a minus 2. So that checks out. However, which is greater, 4a minus 3 or 1, depends on what a is. So we've got a couple cases here. So the first case is if a is greater than 1. Well, that means that 4a minus 3 is greater than 1, and so we denest in this way. 1/2 times square root of 4a minus 3 minus or plus 1. In other words, minus or plus 1 plus the square root of 4a minus 3 all over 2. And when does that equal to our right-hand side of 1 minus or plus the square root of 4a minus 3 over 2? Well, that's when 1 is positive and square root of 4a minus 3 is positive. Again, that's the bottom symbol of our minus plus, so that comes from plugging in x4, the second one. So x4 is a solution, but not x3. That's in that case. Now, the second case, when a is between 3/4 and 1 inclusive, well, that means that 4a minus 3 is less than 1. That means 1's bigger than 4a minus 3, and so our square root of a minus x34 is going to denest to 1 minus or plus the square root of 4a minus 3. In other words, 1 minus or plus the square root of 4a minus 3 all over 2. And does that equal our right-hand side? Well, the right-hand side is 1 minus or plus square root of 4a minus 3 all over 2. They're identical. So in this case, both x3 and x4 are solutions. Let's put all this together and give a summary of our solutions. So if a is greater than 1, then we have two real solutions. X1, which equals negative 1, plus square root of 4a plus 1 over 2, and x4, which is 1 minus the square root of 4a minus 3 all over 2. Now, if a is between 3/4 and 1, I'm going to leave 3/4 out of this for a second. In this little interval here, there's three real solutions. We've got x1, which is always going to be a solution. Square root of 4a plus 1 over 2. x3, which equals 1 plus square root of 4a minus 3 over 2. And x4, which is 1 minus square root of 4a minus 3 all over 2. So what happens when a heads towards 3/4? Well, it turns out when a is equal to 3/4, these are equal to 0, and so x3 equals x4, equals 1/2. And also, this ends up being positive 2. And so x1 is also going to be 1/2. So in this case, there's one real solution. x1 equals x2 equals x3, which is 1/2. Now, less than 3/4, we also only have one real solution, and that's x1, which is, again, it's negative 1 plus square root of 4a plus 1 all over 2. And of course, as we said before, if a is less than 0, then there's no real solutions. So I think that's enough for now. It was neat seeing that we could solve this equation with a more general parameter using factoring the depressed quartic and also checking those solutions with our tool of denesting radicals. Are there quicker ways to do this? Oh, probably. Anyway, see you next time.